Here is a comparison that sounds wrong until it clicks. Fine-tuning a language model is to pre-training what renovating a kitchen is to pouring a concrete foundation. The same word building covers both ideas, but the gap between them is massive. One demands a crew of dozens and months of work, while the other only needs a contractor and a weekend. Yet the AI world slaps those two phrases together and uses them interchangeably everywhere. They are not the same thing. They involve the same basic math using gradient descent to adjust weights, but operate on completely different scales, budgets, and purposes. The gap between these approaches dictates whether you spend $50 million or just $50 on a model project. It is never just an academic exercise. We will walk the entire spectrum, starting with raw pre-training. You will then discover the exact fine-tuning techniques that developers actually deploy today. You begin with a blank neural network holding random weights and zero knowledge. You then feed it trillions of tokens scraped from the open web. This training phase, or more precisely pre-training, is how a language model actually learns to understand language. It transforms raw data into real comprehension. You pull those tokens from books and websites alongside code repositories and scientific papers. The model itself faces a deceptively simple task. It just needs to predict the next token in any given sequence. That one objective applied across trillions of examples forces the model to learn grammar facts, reasoning patterns, and common sense. It quietly builds the foundation for everything that follows. That's it. That really is it. The model quietly learns the hidden structure of how concepts relate and the statistical shape of human knowledge. The real magic happens because of sheer scale. That scale is what makes pre-training extraordinary. We feed it trillions of tokens spanning dozens of languages and domains. Thousands of GPUs run continuously for weeks or months to process it all. The project spends millions to tens of millions. The result is a base model that is powerful, but not yet useful for specific tasks. This model finishes your sentences and answers basic questions while actually reasoning through real problems. It ignores your instructions and might contradict itself. You get raw intelligence with zero manners. The underlying mechanics are almost painfully simple, and that is exactly what makes them elegant. The model grabs a sequence of tokens like the capital of France is and simply predicts what comes next. To get that right, the system quietly maps out everything it knows. The AI maps countries to capitals and instantly recognizes France. It catches the grammatical rhythm of factual statements. It builds a semantic grasp of what a capital means in context. The system links it to government and geography. Early in training, the model memorizes which letters follow which. It learns basic patterns before understanding language. Transformer training reveals that attention lets the model weigh which input parts matter for each prediction. This unlocks flexible context. Later, it picks up word relationships and grammar. It eventually masters complex reasoning. Modern models predict the next word instead of reading text linearly like older architectures ever could. This design choice unlocks speed and scale that previous systems simply could not match. Training splits massive batches across hundreds of GPUs to keep the pipeline full. Each card handles a slice of the workload, so the system scales without slowing down. Model parallelism slices the neural network itself across tensor and pipeline architectures. Gradient accumulation and mixed precision conserve memory, while high bandwidth interconnects synchronize thousands of GPUs without a single lag. The training process is notoriously fragile, and one wrong turn triggers loss spikes or gradient explosions. Those convergence failures erase weeks of work and hundreds of thousands of dollars in an instant. Building this infrastructure demands precision at every layer. You need zero bottlenecks to push data through a single massive run. Fine-tuning takes a pre-trained base model and keeps training it on a smaller, focused dataset to specialize it for a specific task or domain. The model already understands language, so you are not teaching it how to build a sentence. You are teaching it how to apply that existing knowledge to your particular use case. The difference in requirements is staggering. Fine-tuning comes in several flavors. Supervised fine-tuning feeds the model thousands of instruction response pairs to lock in how it follows directions. Reference tuning like RLHF or DPO shapes the model around human preferences. It trains the system to be helpful, honest, and harmless. Domain adaptation feeds the model's specialized text like medical papers and legal documents. The system learns to speak your industry exact language. This is where things get interesting. Agentic training teaches models not just to answer questions but to use tools, reason through multi-step problems, and recover from errors. AI agents that plan, act, and iterate toward goals have exploded in capability. That shift demands a completely new training paradigm. The process trains the model on full agent trajectories. You feed it sequences of thoughts, tool calls, observations, and corrections. Models learn to break down complex tasks and call APIs. They pass structured results and keep looping until the problem is solved. This is not pre-training. It is a highly targeted, fine-tuning exercise built on carefully constructed synthetic trajectories. Teams generate these trajectories using stronger models. They then distill that knowledge into smaller and faster models. The trend is obvious. Local fine-tuning of agentic capabilities on models that fit a single workstation GPU is rapidly becoming the new standard. This setup delivers a real competitive edge. Teams get deep reasoning without any cloud dependency. It is an architectural choice that keeps the core model frozen. The system dynamically pulls relevant context from an external database before each generation step. Strictly speaking, retrieval augmented generation, or RAG, is not training at all. It simply expands what the model already knows. Think of it like handing the model an open book exam. You are not testing its memory. You are measuring how well it uses fresh information. You keep hearing them paired together so naturally, you have to ask when to actually pick one over the other. Feed it current data market prices or daily updated docs, and RAG is your cheap right call. You want the model to match your company, tone follow specific formatting rules, or speak your domain jargon, and fine-tuning is your answer. RAG handles facts that change. Fine-tuning locks in behavior that sticks. Fine-tuning wins here because it permanently internalizes those patterns. Up systems combine both approaches to stay sharp. They fine-tune the model for perfect style and structure, then layer in RAG for accurate live facts. Forget updating every weight because that chokes your memory. LoRA locks the original model and trains tiny matrices instead. When you actually fine-tune, you will almost always reach for LoRA. Low-rank adaptation just stacks these adapter matrices right on top. The payoff is huge. You capture 95% of the fine-tuning benefit while burning just 1% of the memory. QLoRA takes it a step further by quantizing that frozen base model first. Now, you can fine-tune serious models on a single consumer GPU. It like AF. Deploy it strictly for task-specific work to slash your compute costs. The biggest mistake is overtraining. Fine-tuning costs pennies, so you will want to crank up the epochs. Push past that sweet spot and you trigger overfitting. The model starts memorizing your examples instead of learning the actual pattern. Track your validation loss instead of just staring at your training metrics. These are not rivals but steps on a single spectrum. Knowing where each one fits in your project is exactly what separates teams that win. Retraining builds the brain. Fine-tuning teaches it manners. RAG hands it a reference book while agentic training teaches it how to use tools. They ship from teams that burn serious compute. That's the full picture. If this made it click, tap subscribe. There's a new AI explainer here every day. And tap the video on screen to keep going. See you in the next one.